Okay, let's get started. So last time I hopefully convinced you, at least in a sort of hand-wavy way, that if we form cosmic strings in the early universe, then we set up some sort of interacting network on which there's roughly one Hubble length worth of string per Hubble patch, and this remains the case as the universe evolves forward. As a result, the total energy density in these strings as a function of time goes like the string tension times Hubble parameter squared. And writing the Hubble parameter in terms of the total energy density of the universe, rho total, this means that the string network always carries a fixed fraction of the total energy density. On the other hand, domain walls, just because their dimension is different, end up having an energy density, a similar scaling solution in which there's roughly one Hubble area of domain wall per Hubble patch, which leads to this sort of energy density in total, and correspondingly, rho domain wall divided by rho total increases as a function of time. Today I'm going to sort of finish this story by talking about monopoles, and then I'll go through a few different observational signals of, well, these types of defects. For the observational signals, I'll be a bit hand-wavy and just give you the rough order of magnitude signals that we expect from the different types of sources. If you're then interested in one particular one, or even you want to work on something like this, you can, of course, investigate in more detail and see all the complicated things people have done in practice. But I think getting a rough idea of the scales is perhaps most important. For monopoles, perhaps the most natural thing to think about is some monopoles arising from a gut symmetry breaking transition. As we've already seen, if we want to get out U1 hypercharge, and we want to start with a simple gut group, then we inevitably get out monopoles. And the masses of these monopoles, let me call this mm, up to factors of pi, typically something like this, where here mx is the scale of the gut symmetry breaking, which you'd usually think might be like 10 to the 16 GeV or something like that, and g is the gauge coupling, roughly, of the gut group. So of course these monopoles would be extremely heavy. They're produced by the similar mechanisms that we talked about already for strings and domain walls, just by causality. As a result, we expect at the time if these monopoles are produced them to have a number density, let me say at the time of formation, that is roughly bigger than 1 per Hubble patch at the time of formation. And if you've studied dark matter, or if not, as you'll see probably in your dark matter lectures in a couple of weeks' time, when keeping track of the number density of, well, at least point-light particles in the universe, what is usually most convenient to think about is the number density divided by the entropy of the universe. So this means that at least initially Nm at time of formation of entropy is going to be roughly this divided by the temperature of the universe, if I say that we're in radiation domination, cubed. So that works out to be T at T formation over M Planck cubed. Putting in temperatures of, say, 10 to the 16 GeV, you see that actually this is actually a pretty large number, so you might say 10 to the minus 6. Then the crucial question is what happens to these monopoles once formed. Unlike strings and domain walls, we don't actually get driven to this attractor scaling solution where we have one monopole per Hubble patch. I think one way to understand this is just on dimensionality. So if I have 2 long strings per Hubble patch, there's an order 1 probability that these things will intersect. Likewise with domain walls, if I have 2 large domain walls, actually there the chance is it's even more likely that they will intersect. Whereas if I have 2 monopoles floating around in what is the present universe, the chance of these things intersecting, having paths, world lines that intersect, is almost 0. People have done more detailed analysis, and indeed it turns out that if I start with a very large abundance of monopoles and I evolve forward in time, maybe some annihilations will happen. There'll be some monopole, anti-monopole pairs that annihilate. But typically you get out that this number remains greater than 10 to the something like minus 12. And then it depends a bit on the mass of the monopoles. Let me normalize that to 10 to the 16 GeV. Okay, so again, for people who know a bit about cosmology, you'll see immediately that such monopoles would have an abundance in the present day universe that is pretty comparable to baryons, at least if their masses are comparable to 10 to the 16 GeV. This is spectacularly ruled out. We know that we certainly don't have this many monopoles floating around in the universe. There's all sorts of different observational constraints. One is simply from the energy density that they would contain, which is far too much compared to what we know the composition of the universe is. There's also direct searches. You can just look for these monopoles flying through the Earth. There's maybe more interesting theoretical effects that if you have a gut monopole, these can lead to proton decay as a proton passes through the core of a monopole. It can actually decay in some grand unified theory much faster than you would expect. And this is actually particularly important if the monopoles were captured in neutron stars, say. But anyway, regardless of which of these particular observational constraints you care about, gut monopoles existing in any significant abundance in the present day universe is spectacularly ruled out. And indeed, this was, as I mentioned already, one of the motivations for inflation. If you wanted to, I'm sure you could easily write down some theory with some hidden sector that led to monopoles. Maybe they could be dark matter, they could probably lead to new observational signals. One always has this freedom. But let me instead now go through some of the observational signals of cosmic strings or domain walls, which are perhaps more interesting and maybe more experimentally relevant for what is happening in the near future. So maybe just to give a bit of historical perspective, actually the original hope of cosmic strings would be that they would lead to cosmic structure formation, so result in the galaxies and other cosmic structures that we see in the universe today. I think actually this was in some ways quite a nice idea. On the other hand, unfortunately, it just doesn't work with observations. So the basic idea is that if I have this sort of string network, then if I have some string loop, dark matter, for example, would accrete onto the area that the string loop is, or the part of the universe the string loop is in, just by gravitational effects. And these small fluctuations induced in the dark matter would then accumulate more dark matter, density fluctuations would grow, and this could become a galaxy. Likewise, if I have some long string that is moving relativistically, when you go through the details, this leaves some wake of high energy density behind it in some sense, that again accretes dark matter onto it and could form structure. The problem with this is that by now people have looked at the density fluctuations in the universe in great detail. We see that they are adiabatic fluctuations. This means that they are perturbations in all of the components of the energy density in such a way that the relative energy in each of the components stays unchanged. It's just an overall fluctuation. We also have a spectrum of density fluctuations that is initially, before they grow, almost scale invariant. And perhaps most important for strings, if you look at the density fluctuations, then these are, at least initially, almost Gaussian. So effectively, you can think of the density fluctuations being initially just some sum of plane waves with uncorrelated phases. Meanwhile, the cosmic structures that would form from strings have none of these properties, so there's no hope of using strings for structure formation. So structure formation instead these days only gives us limits on the string tension if we have such a string network around, with g mu being roughly less than 10 to the minus 7. At this point, you might say, okay, we give up. The original purpose of cosmic strings was this. It doesn't work. Why continue? On the other hand, maybe this is a bit too hasty. It might be that the original thing that people thought of cosmic strings for doesn't work out, but there could be other reasons to think that they exist. And perhaps, at least for me, and for maybe some people in the community, one of the interesting reasons for cosmic strings is post-inflationary axions. Slightly preempting what Pratik will probably tell you in the next 2 days. Suppose that I have some axion that arises from spontaneous breaking of some global U1 symmetry, and suppose that this breaking happens in the early universe after inflation. Then the cosmology of this theory is going to look something like this. When the temperature of the universe is high, roughly of order the axion decay constant, which maybe is, say, 10 to the 10 GeV, I'm going to get a network of cosmic strings. This will then evolve until the universe drops down to a temperature that is roughly equal to lambda QCD. As you've just heard, or as I'm sure you can imagine, the properties of the axion, if it's a QCD axion, are associated to the properties of QCD. When QCD becomes strongly coupled, actually the axion will get a mass. At this point, like I said in the last lecture, the axion potential will lead to domain walls, which will in turn destroy the string network, at least in the minimal theory with n domain wall is equal to 1. So after this time, we have no more topological defects, and all that we get in redshifting to the present day, let me call that T0, is just relic axions left over from this era. These relic axions can then play the role of dark matter. This is pretty nice. We've introduced the axions to solve some separate problem, the strong CP problem. And then we automatically get our dark matter candidate out. Another nice feature of this particular scenario is that it's reasonably predictive. So because we know how the string network evolves and we know how domain walls evolve, we can predict how many axions are produced. Moreover, again, slightly probably preempting what Pratik will tell you, we know that actually the mass of the axion is fixed in terms of parameters of QCD. Here, very schematically, I've written it as lambda QCD. Really, it should be the mass of the pion with the pion decay constant, with the only unfixed parameter being the axion decay constant, which is the scale of this U1 symmetry breaking, or the periodicity of the axion field with some normalizations with n domain wall. This is good. It means if we can predict the number of axions that are produced by the strings and domain wall network, and we know their mass, if we can predict their mass in terms of the axion decay constant, and we know how much dark matter is floating around in the universe today, then we can predict the axion decay constant, or equivalently its mass. So there's something to search for. So omega dark matter today implies the axion decay constant, which is equivalent to the axion mass. And then one could imagine going out and searching for it using whatever your preferred axion direct detection search is. Let me just give some sort of schematic cartoon of what the calculation, or what such a calculation involves. The destruction of the domain wall network is pretty complicated. There's many different scales in the problem. So I'll just focus on the part from when the strings are formed to when the domain walls form and destroy the string network. So as I've written up there, the energy density in the string network is given by that expression. But we also know that if we have a single long string in some Hubble patch, and I forget about the string interactions, all of these processes that are destroying string length, then the energy density, let me call it, of just a string that is fixed in co-moving coordinates with no interactions, redshift as 1 over the scale factor squared. So it doesn't redshift as matter, but because it's also getting stretched in one direction, the energy density redshifts slower. And in radiation domination, let me write this as 1 over T, whereas the energy density in the network goes as 1 over T squared. Is there a question? Okay. So the energy density in a fixed string would redshift much slower than the energy density of, or decrease much slower than we know the energy density of the network decreases. And in turn, this means that actually for this string network to maintain the scaling solution, it needs to lose an order 1 fraction of its total energy density per Hubble time. That means in turn that the rate of energy emission of the network to these axions that will become the dark matter is going to be roughly equal to, let me put back in this order 1 parameter, psi times the string tension times, now we need extra factor of h, but this is happening, this is the total energy being emitted per Hubble time, so we then divide by energy density, so h squared. And now that we know, or can at least predict, the rate of energy emission to axions, we can in turn predict the total energy density that gets put into axions. So this is integral up to t, dt prime, gamma of t prime, just integrating over all times. While all of this is happening, the axions are relativistic. Their mass hasn't turned on yet because we're still well above the QCD scale in terms of temperature. So the energy redshifts this way. Now, in practice, if one wants to get a reliable or accurate calculation for the energy density in the dark matter axions, we also need to know this parameter xi precisely. If you remember, for global strings, this tension mu had a log divergence, which was evolving during the universe, so we need to take that into account, and so on. The other ingredient that we need is also the spectrum of axions that are produced. But once we've got that ingredient, we can then predict in dark matter. And as I've mentioned, this in turn gives us a prediction for the dark matter axion mass. Okay, I won't say any more about the computation. In some ways, it's kind of straightforward from this point. The only hard thing is really pinning down all of these predictions for especially the spectrum, but also the string density and so on. And maybe just to say that this is an area where there are still uncertainties in the literature, disagreements, and so on. Okay. Another interesting possibility is that a string network or a domain wall network could emit lots of gravitational waves. These would then float around in the universe, not interacting with anything until the present day, when they would form some stochastic background that we could search for. Yeah. This is this order one parameter representing the number of strings per Hubble patch. If you want to get some precise calculation, you need to know that, but schematically, it's okay, let me just give some indication of how we can estimate roughly how many gravitational waves are going to be produced by a global string network. So to do this, I can make use of the Karl-Brumond plus Nambu-Goto effective theory that I introduced earlier. And again, very schematically, if you look at that effective theory, the equation of motion of the string in terms of its target space coordinates is something like its tension, then x mu double dot minus x prime. These are derivatives with respect to the world volume coordinates. Some numerical factor that doesn't matter, the axion decay constant, and then axion x dot x prime, where, just to remind you, I've introduced that the axion is represented by this field A with the identification that F, which is equal to dA, is very schematically the derivative of the axion field. Yes, yeah, so indeed, if we look at the equations of motion, we can also predict the emission of axions by the network. So we have the equation of motion is something like d squared A, which is now sourcing the axion field, is, let me put the 2 pi in, it doesn't really matter, but just for consistency. Then here, let me write d sigma being the world sheet coordinates, not the string tension, but just to keep slightly unpleasant notation, but x prime. Okay, I'm not being careful with these indices, but at least schematically it's correct. Stuff. So at least within the effective description, we have an equation that is showing how the axion field is sourced by the string network. This effective description inevitably breaks down if we have two strings that cross each other, or if we have regions of strings with curvature that is large compared to the string thickness, but in some processes it's valid. Now the trick that we're going to play to get our gravitational wave emission is that we have a similar equation for the sourcing of gravitational waves. So if I write or expand the metric that g mu nu is equal to the flat metric plus gravitational wave part. Again, very schematically and not being careful with indices. The equation sourcing the gravitational waves looks something like, I'll put the 16 pi in, it does no harm. Times the stress energy tensor T mu nu of the string. So these you can just derive with a few lines of work starting from our effective theory that we introduced. So far we haven't really gained anything because, as you can see even from the sketch that I did before, the actual string network in the real universe would be extremely complicated. The trajectories of strings would be, well, impossible to actually pin down what they would look like in terms of x mu and so on, let alone actually solve these equations to find how much axion field is sourced, how many gravitational waves are sourced. However, the useful thing about this is that we can see where all of the dimensionful stuff is entering. So everything here just depends on the shape of the string trajectory. Similarly here, all of the dimensional stuff comes about because this is something like schematically 16 pi g times string tension times dimensionless stuff. Which then in turn tells me that the rate of energy emission to axions by the string network is going to be FA squared times rated as 1. Whereas the rate of energy emission to gravitational waves goes like g times mu squared times order 1. So this FA squared is coming about from this equation because we know the energy in the axion field goes as dA squared, which picks up a FA squared. Meanwhile, for gravitational waves, we have from this equation that H goes as g times mu. And we know that with this convention of the metric, the energy in gravitational waves goes as, let me say, dH squared over g Newton. Okay, any questions leading up to this part? Okay, good. Okay, then the final trick that we can play is that this tension is roughly going to be equal to g FA squared times some logarithms. We're always going to be interested in values of FA that are very small compared to M Planck. That means that the vast majority of the energy density that the string network is emitting is going into axions rather than gravitational waves. In fact, we'd already assumed that when we calculated gamma axion up here. This in turn means that the relative energy going into gravitational waves compared to axions is going to be some order 1 numbers times squared. Sorry. Is given by an expression of this form times some order 1 number. And plugging in our expression for gamma axion, this is then mu times h cubed, sorry, h squared. Yes. Sorry, dimension 6, dimension 4. Maybe it's h squared. Okay. Yeah, yes, dimensionally. Dimension 4, yes, I think h cubed. Thank you. H cubed, thank you. Okay, so with that, we've got some prediction. Of course, you'd want to check it in numerical simulations. But assuming that it holds and redshifting to the present day, we get an energy density in gravitational waves that depends on frequency, of course, but is something like 10 to the minus 15. And then let me normalize the axion decay constant Fa by 10 to the 14 GeV to the 4. So we have a prediction. For the QCD axion with Fa being roughly 10 to the 10 GeV, this is unobservable, at least in any plausible near future experiment. On the other hand, you could imagine there's some axion-like particle, in which case Fa could be much larger, potentially this could be detected. Maybe the most interesting thing about these gravitational wave signals is that if we look at the frequencies of the gravitational waves today, well, at the time they're emitted, we expect the gravitational wave frequencies to be comparable to the Hubble scale because this is the only scale in our problem. So they start off at h at, let me say, the temperature of the universe when the gravitational waves are emitted. Then we just redshift the frequency to the present day, so we do T0 divided by T emission. And plugging in numbers, this is something like 10 to the minus 6 Hertz, temperature of the universe at emission divided by GeV. And if extremely schematically, I sketch what experiments might be able to do. Very roughly, this is something, numbers like 10 to the minus 10, 10 to the minus 14. CMB observations potentially could search for gravitational waves with frequencies of like 10 to the minus 17 Hertz. Pulsar timing arrays, maybe something like 10 to the minus 10. Meanwhile, the LISA satellite, which hopefully will be launched in the not too distant future, frequencies of 10 to the minus 2 Hertz. And then we have things like advanced LIGO at slightly higher frequencies. This is nice. It means that if we have some experiment like LISA that is potentially probing frequencies of 10 to the minus 2, that would potentially be testing or searching for gravitational waves produced when the temperature of the universe was something like 10 to the 4 GeV, potentially even slightly higher with future experiments. So maybe these sort of gravitational wave signals could give us some window back into the early universe. Of course, there are many, many challenges to be faced by these sorts of experiments. There's big astrophysical foregrounds that one has to worry about. But Yes, definitely. So I think to order of magnitude, I think it does get the axion emission from the network. The problem is if you want to know things like the detail of the spectrum, which then I slightly glossed over, but enters the computation of the axion number density. For gravitational waves, the spectrum seems kind of safe, and we just need it's always peaked at the Hubble scale. It's roughly right, yeah. Well, in some sense, I've already put in the knowledge that of how much energy is going into axions in this argument, which allowed me to skip some detailed knowledge that I don't have access to here, but roughly orders of magnitude, it's all kind of there. And for these gravitational wave signals, really all we're aiming for is to get right ballpark kind of figures. Yes, indeed. So there's some very mild log tilt from this, but another nice thing, thanks, one of the things I should have commented is that if we did see such a signal, it would span across all of these experiments, at least assuming a standard cosmological history. So this is maybe something nice. You might hope that if you did believe that the signal and pulsar timing arrays in nanograv was a string network, well, you just wait for LISA to be built, which will take some time, but you have some prediction. You see something there with a comparable amplitude. Maybe you celebrate, you see nothing, you say, well, it's supermassive binaries. Yeah. Any other questions on this part? Cool. One can also ask what happens with a local string network. So this was a string network arising from a gauge symmetry. In this case, there's no light degree of freedom, analogous to the axion. So this kind of argument with the effective theory just doesn't work. We know that still in this case, the network has to emit an amount of energy density per unit time into something. Let me forget this order one factor and just write it as string tension times h cubed. But actually at this stage, the current level of understanding is we don't know where this energy goes. The two options are it could go into heavy degrees of freedom. So this would be, for example, the massive vector in this theory, which has a mass of roughly the symmetry breaking scale, assuming no small gauge couplings, or the radial mode in the original theory, which has a similar mass. The other option is that all of this, or most of this energy, could go into gravitational waves. In some ways, either of these are sort of plausible, but also sort of implausible to be the dominant energy loss mechanism. So the heavy modes, you may say, well, they're strongly coupled to the string. After all, the string is made of these degrees of freedom, so they should be easy to emit. On the other hand, if the typical curvature scale of the string network is of order Hubble, and Hubble is far, far less than the symmetry breaking scale at the times that we care about, maybe it's extremely hard to emit heavy degrees of freedom. Just from an effective field theory point of view, would say that the effective action of the string is now Nambu-Goto. We've completely integrated out everything heavy, so there's nothing it could emit to. In that sense, gravitational waves are plausible because they're light, they remain in the effective theory. On the other hand, G Newton is extremely small compared to V squared, so maybe this is also hard to emit, just because Planck is much less than 1. And I simply can't tell you the answer at this stage because no one really knows convincingly. If I do numerical simulations of, say, the abelian Higgs theory that gives rise to these strings, then I find that all of the energy goes into heavy modes, but I can only do simulations at small scale separation, so I can't separate Hubble from the string core scale very much. So maybe you would say this is just some transient effect. On the other hand, if I do simulations directly of the Nambu-Goto effective theory, then I see that all the energy goes into gravitational waves, but actually that was completely automatic. By construction, I've created an effective theory in which there is only gravitational waves that can be emitted, and there are no heavy modes, so that's not really telling me anything either. Yeah, I can't tell you the resolution of this because no one knows, but if you could come up with a convincing argument, then actually this would matter a lot. Even the pulsar timing array collaborations currently use some models, some guesses, and they have a big uncertainty between these two different sources or these two different emission processes. Maybe one thing I can do just to give you some idea of the scales or the orders of magnitude is to say, let me take the most optimistic case for observation of gravitational waves, that all of the energy goes into gravitational waves. Then very roughly would have that at the time of emission, the energy in gravitational waves per log frequency interval would be something like mu times h squared, now not h cubed because I'm looking at the energy emitted per Hubble time, which corresponds to one log folding of space and frequency. And then just redshifting to the present day, we would have the energy spectrum of the gravitational waves would be normalizing relative to the critical density of the universe today, 1 over rho naught. Mu putting in that, let's just do emission during radiation domination to keep things easy. Temperature at emission 4 over m Planck squared. That's coming from the Hubble parameter. This is just the Hubble parameter squared here. And then with the redshifting factor to the present day, which is T0 over T to the 4. Which is roughly equal to omega radiation. This factor of temperature of the universe today to the 4 divided by energy density of the universe today is up to factors of pi squared over 30, which is close to 1 omega radiation. Then with a factor of string tension over m Planck squared. Omega radiation is something like 10 to the minus 4 roughly. So you see that if we could get gravitational wave searches down to omega gravitational wave of order 10 to the minus 40, potentially we could be probing gravitational wave emission from string networks with string tensions of something like 10 to the minus 5 m Planck squared. And this is potentially interesting because we've seen already that we could, in the early universe, produce such string networks if there was some symmetry breaking at a high scale. Of course, sorry. Yeah. Yeah. Yep, exactly. You could try. I think you can certainly estimate the rate of intersection. Probably what is harder is to know quite what happens at the moment of intersection, how much energy gets emitted. So imagine, let me give maybe the most dramatic scenario that could most easily emit heavy modes is, suppose I produce some loops and that these self-intersect pretty efficiently. You can imagine that each time the loop oscillates, maybe I halve the string length in each loop. I produce two loops, and then I would cascade energy to very small spatial scales, high momenta, very efficiently. And in that case, it's maybe plausible that lots of energy goes into heavy modes. On the other hand, if the typical loops that I produce don't self-intersect very often, they would keep oscillating without missing each other, without crossing each other. And at that point, maybe this energy emission to, or this shift of energy to higher scales is much slower, and actually the gravitational wave emission would be more important. So I think in some ways it just depends on like the details of these loop oscillations. Any other questions on this part? Nope. Let me just mention also that you can get gravitational waves from domain walls. The story is very similar there. Although actually in the domain wall case, I think the standard understanding is that most of the energy goes into heavy modes there. This is perhaps plausible if I have an oscillating loop. I can imagine that as it oscillates, it doesn't self-intersect. On the other hand, if I have some closed region of domain wall, I can't make it oscillate without self-intersecting, so perhaps the heavy modes are easier to excite there. Okay. Another actually very model independent way that I could search for cosmic strings is through their gravitational effects. I mentioned briefly that around a string, actually the metric takes an interesting form with a deficit angle. So if I have some string here, then locally to an observer just sat around the string, space-time looks flat. But if I do a loop around the string, then I notice that I'm missing an angle in space-time that is 8 pi g times mu. This means that if I sit as an observer over here, and I'm looking at some distant star that is, say, sat here, on the other side of the string, actually what I'm going to get is some sort of lensing effect. So light ray, if I draw like this, okay. If I say that this missing angle in space-time, delta theta, is given by this angle, of course I've blown it up dramatically in terms of scales, then what the observer sitting here actually sees is two images of this star or galaxy, one here, effectively both reaching us along these light rays here. Effectively, because light from this star that goes off in this direction can get lensed back towards the observer by this deficit angle. One can just look in the sky for such lensed galaxies. The analysis is made more complicated because, of course, there's many other objects floating around in the universe that can lead to lensing. Perhaps the most dramatic signal that you could possibly hope for in these kind of scenarios is that if I did have some long string somewhere across the sky, I would correspondingly get many pairs of lensed galaxies along this one-dimensional direction in space. Actually, current limits from these kind of searches are something like g mu less than roughly 10 to the minus 7-ish. There are some papers that I reference in the notes hoping or claiming that one could go down to, say, 10 to the minus 10 or 10 to the minus 12 in this parameter. I don't know if those are maybe a bit futuristic, but it could be interesting. Yes. Yes. Yep, absolutely. So another complicating factor in this bound is you need to know the distribution of strings in the universe today, which again runs into all of these complications of how do you do the numerical simulations, how do you know quite what the loop distribution is, and so on. Yeah, indeed. Indeed, so for anyone who is sufficiently energetic or talented, there are a lot of unresolved issues here that you can attempt to fix and would be potentially actually important for observations. Another more model-independent effect, but which is potentially very interesting, is if I have a global string that is coupled to photons in the way that you would think that an axion string generically is. Here, for lack of time, and because actually it is Pratik's work, I'm going to defer to, if you're interested in the effects of global strings coupled to photons, ask Pratik in the question and answer session. And I shift the, I therefore save myself time. Just as one final observational possibility, actually, I think quite an interesting way that you could form black holes is from domain walls in the early universe. Maybe a lot of people in the past have considered black hole formation or primordial black hole formation coming from inflation, but this is not the only possibility, and indeed this may even be in some ways a nicer possibility. So to indicate the kind of physics going on here, let me suppose that I have some closed domain wall, and let me imagine this sort of picture that I was saying before, where we have a small energy bias between the two vacua, with the domain wall interpolating between here and here. Then again, my artistic abilities are sort of limited, but let me imagine that I have some closed domain wall of the false vacuum, which is in the process of collapsing. Then the energy density, or the mass associated to this closed domain wall, and we call it m star, is going to get a contribution from the surface tension of the domain wall. So that will be like 4 pi sigma r star squared, where now I'm saying that this is the typical radius. And it will also, relative to the true vacuum, have some contribution just from the vacuum energy of the region. So 4 pi v epsilon r star cubed. So this is how much energy density I have in my closed domain wall, and now I want to know whether this object can form a black hole. So the object will inevitably form a black hole if it enters its own Schwarzschild radius. Which is roughly g times m star. So the crucial number, or the crucial ratio here, is the size of the domain wall compared to Schwarzschild radius, Rs over R star. Which is gm star R star roughly equal to sigma star epsilon. Which is given by an expression of this form. So what does this number p tell me? Well, if p is roughly 1, then it tells me that immediately at the starting time when I begin to look at this domain wall, it is basically almost a black hole already. On the other hand, if P was much less than 1, my domain wall is much larger than a black hole, and in order to actually form a black hole, it would have to collapse down a long way, but it'd also have to collapse in a way that didn't lose any energy density into friction, into thermal bath or whatever, and it would have to be sufficiently spherically symmetric that it remains roughly, let's say, spherical down to this tiny radius, down to its Schwarzschild radius, rather than being some more complicated shape that then would miss getting inside the required small radius. So as usual, complicated simulations are probably needed to actually pin this down, but at least it's pretty plausible that if this number P is roughly equal to 1, we're going to get a lot of black holes out of this system. In general, for large R star, it's probably easier to achieve this by having this second term here coming from the overall region of false vacuum being roughly 1. And in particular, if we have that the energy difference between the two vacua is sort of comparable to the total energy density in the universe at the time, if V epsilon is, say, roughly equal to rho total, then G times V epsilon R star squared is roughly equal to 1 over m Planck squared rho total times this first part is Hubble parameter squared star squared. And this now tells me that if I start off with a bubble that is almost of the size of the Hubble radius, which is sort of plausible since this is the size of all of the domain walls in the network, then I could relatively easily, let me say, form a black hole, at least provided this energy difference between the two vacua is sufficiently large. In fact, actually, this could even occur for the QCD axion in some scenarios. You'd get out some energy density today in black holes that is maybe roughly of order 10 to the minus 7. Again, there's some references in the notes if you're interested in this as a black hole formation mechanism. Okay. Yes. Sorry. Yeah. Yes, that's an interesting question. That will depend on the details of the initial domain wall that collapses down. Naively, yeah, I think it depends on, it will probably depend on the details and would have to study it pretty carefully. That would certainly be very interesting if you had some way to distinguish black holes formed this way from primordial black holes from inflationary fluctuations where much more is known about their particular properties. I think one could attempt to do simulations for that, but it's... Okay, so I think this is all I will say about the observational signals of topological defects. I hope that I've at least given the impression that there are many different avenues, although there are many uncertainties. Instead, for the last roughly half hour, I'll do a bit of an introduction to non-topological solitons now, which will be continued in the later lectures. Maybe before that, are there any other questions on the observational signals? Yeah. If the, what, sorry? Ah, the no hair. Oh. It probably depends on the details of the underlying theory that gives rise to the domain walls. You could, I'm sure you could cook up some theory where there was something interesting going on there with the details of the symmetry breaking and so on. I don't. Sorry. Yes, there may be. Yeah, but that could potentially change the evolution of the. Yeah, the very early evolution of the black hole. Maybe not completely related, but let me just mention also I've glossed over various complications that this will be happening in some thermal background as well. It's not that I just have some isolated domain wall sitting there, so there will be additional effects. But yeah, very good question. Anyone else? Yes, okay. So briefly in the last lecture, I mentioned things, said vague words about D-brane inflation and string theory, cosmic string axions, and so on. I guess certainly the axion quality problem is something one has to address one way or another. The one fast way around it would be to say that I could imagine some composite axion theory, in which case the details of the cosmic strings would be more complicated. Their cores wouldn't just be some scalar field going to the top of its potential, but some strong dynamics and so on. In which case, I think most of what I have said would hold. If you believe in a genuinely extra-dimensional or string theory axion, then the nature of the axion strings is going to be very different. I think this is potentially interesting. You might imagine some multi-scale thing where the core of the string, which is giving the dominant, which would give it the dominant contribution to the cosmic string tension, is associated to genuine fundamental string theory stuff, but you still have the axion winding around. Yeah, many interesting questions, I think. Anyone else? Okay, if not, let me give a very brief introduction to topological solitons. So these are similar to topological solitons, but instead of being stabilized by boundary conditions, they are stable for some other reason, which is typically just energetics. This usually arises because we have some conserved charge in a theory. And the soliton configuration is the lowest energy field configuration carrying a given amount of charge. And in particular, a necessary condition to get a non-topological soliton is that my object, let me just think of solitons that are particle-like in 3 space dimensions, must be stable against emitting a single quanta carrying a whatever this conserved charge is. If this sounds a bit exotic or unusual, then just think of nuclei. So at least if we ignored electromagnetism and similar things, then you know that we have some conserved charge, at least to a very good approximation in the standard model, which is the baryon number. And if we fix some amount of baryon number, then the lowest energy configuration that we can create carrying that amount of baryon number is typically either a single big nuclei, or if we go to sufficiently large nuclei, it would be a few different ones with smaller baryon number each. And non-topological solitons are pretty much the same kind of idea. So simplest example is nuclei, at least up to iron. On the other hand, of course, calculating in strongly coupled theories, including nuclei, is tricky. One, I would claim a nucleus is, in some sense, a non-topological soliton. Maybe I'm being slightly more too general with my wording, but at least in many ways, the key features, I think, are basically there. Actually, the two examples that I'll talk about in these lectures are, first of all, what is known as Q-balls, and then I'll talk about axion stars. So Q-balls were invented or discovered, if you like, by Coleman, actually these days quite a long time ago. And in some ways it's a slightly unusual topic to pick to lecture about because by now it's kind of historical. On the other hand, they have a lot of interesting features that are shared by the non-topological solitons, and they're in some ways just like really nice, interesting theoretical objects. So I think it's worth going through them. Okay. Let me just use the last 15 minutes to set up the basic situation. So let me consider a theory of a single complex scalar, phi. And let me suppose that this theory has a U1 global symmetry that is preserved by the potential of phi. Just exactly standard form. And now the slightly unusual feature that I'll demand is that the potential U of phi, maybe I can write it as modulus since it respects the global symmetry, has to increase slower than m squared. Sorry, slower than phi squared, at least in some part of field space. So to put that more precisely, we demand that the minimum value taken by U of phi, the potential over phi squared, is given by U of phi over with some value of phi naught that is not equal to 0, and that this is less than m squared, where m is the mass of the excitations around the space-independent vacuum. So what this condition means in practice is that suppose I have my usual some potential like this, or suppose that this is the line phi squared, m squared, phi squared. I demand that somehow I create a potential u of phi that close to the origin maybe looks like this, but then dips below before eventually going back up like this. And if you have this sort of shape, then there will be some value roughly in this part of field space where I minimize this ratio and indeed satisfy this condition. You can immediately see that if I just have a single complex scalar field, there's no way I could satisfy this condition with just a renormalizable potential. If I have a quartic coupling, that better be positive, otherwise my Hamiltonian is unbounded below. But then if I have a positive quartic coupling, I will just continue growing in this direction. But I could just think of this as some effective theory with some additional higher dimensional operators, or I can create some more complicated theory that contains, as well as phi, some additional degrees of freedom, and then it's not hard to find suitable potentials. For all that we will say, it's enough just to keep u of phi just in this general form. You might already actually be able to guess how a non-topological soliton is going to come about from this condition, especially given what I already said about the object being stable against emission of a single quantum. But let us see in detail how this happens. So in particular, what we want to do is, let me just do classical field theory, search for solutions of the classical equations of motion that minimize the total energy, but with the charge Q associated to this symmetry fixed. So the charge Q, just as usual, integral dq x j naught d cubed x phi dt phi star minus phi. I can do so by introducing a Lagrange multiplier. So let me define this function curly e as a function of omega to be the usual energy of the field configuration, but then with omega as a Lagrange multiplier. So omega q and now I've been slightly imprecise with my notation, but I hope it'll be okay. In this expression, I'm thinking of Q as just being some fixed number that I'm fixing from the outside. I'm putting this much charge into my system, rather than being given by this particular expression for the field configuration. And then after a few lines of algebra, starting from this expression for the charge and the usual expression for the energy density of the complex scalar field, you can show that this function curly E of omega is given by this expression. Sort of similar to our analysis of domain walls and so on. If we look at this and we want to minimize the energy with respect to both the field profile phi and also the Lagrange multiplier, then this term being positive definite and being the only thing that has any time dependence in it, we can just set to 0 or force to be 0 by choosing a suitable ansatz. So let me write that phi is equal to e to the I omega t, and then I'll use some curly phi, which is now just a function of the space coordinates. Then you can see that if I take such a form for phi, this first term will go away, and everything that is left will have no time dependence. And also, without loss of generality, we can just take this curly phi to be purely real. The imaginary part won't play any role. Okay. And it's also useful to note that evaluated on this particular solution, curly phi, we have that the charge of a configuration is equal to 2 omega integral d cubed x phi squared. Okay, and finally, this is the expression we get that we need to minimize with respect to curly phi and also omega. Let me first minimize this with respect to phi, and I'll make the ansatz or the assumption that the solution for this minimization problem has O3 symmetry. So I'm going to look for some field configuration that is symmetric in the 3 space dimensions. Coleman proves that this is indeed the solution of lowest energy in complete detail, but it's a long and in some ways quite technical proof of a result that in some ways is quite intuitive. So this one we already know because, so yeah, if we can, sorry. So yeah, we want this term to be, the best we can do with this term is set it to be equal to 0. And then any additional time dependence we put into psi would only make this term larger, so yeah. With this O3 ansatz, we can write that psi is just a function of r, where I'm choosing to put my object or soliton centered on the origin, and r is just the distance in space coordinates. So then what I need to solve, let me put it at the top. Once I go into spherical coordinates, to is this equation, and the boundary conditions I need are given the spherical symmetry. First of all, the solution must be regular at the origin, which means that dr phi at 0 is equal to 0. And I also want that the total charge of the configuration, wherever it is at the top there, must be finite. So that tells me that limit as r tends to infinity, phi of r is equal to 0, or sufficiently fast. This is good. We've now got ourselves down to an ordinary differential equation that we want to solve. And if you remember back in the lecture on domain walls, we were solving similar equations of motion. And just like in that case, what we can do is if we look at this, we can identify r as being effectively like a time coordinate, such that this reduces down to Newton's law for a particle moving in some potential. And just like in the domain wall case where we flip the potential, we now have that this potential is half omega squared squared. Just from the normalization of the gradient term, we also pick up a factor of a half on the potential. Okay. Let me also define some parameter omega naught to be equal to square root of psi naught squared, where this psi naught is exactly the psi naught that we introduced before. Sorry, phi naught is equal to modulus of phi naught. And just to write that out again, since it's important in the derivation. This is defined such that minimum of okay, now exercise for you overnight. Let me suppose that this Lagrange multiplier that I introduced, omega, which appears in the potential, satisfies the condition that omega naught squared is less than omega squared is less than m squared, where again m was just the mass around the vacuum. Let me get the factors of 2 correct, just Why is it making it harder for you? Okay, so your challenge is to see if you can prove that a solution to that ordinary differential equation star up there, satisfying those boundary conditions, necessarily exists, with this condition satisfied and the potential satisfying this condition. The hint is to think in terms of a particle moving in a potential, and also notice this second term on the left-hand side looks a bit like a friction, but quite an unusual form of the friction. Okay, so I will leave that until tomorrow morning when I will tell you the solution. Thanks.